Hi, I'm Dr. Brian Mendez, the Planetarium Director at the Lawrence Hall of Science at UC Berkeley. Today I'm going to tell you about how to model the phases of the moon in your classroom with a simple setup. This can be an extension to an earlier activity that is described in another video called Mount Nose. The materials you need are a light bulb to stand for the sun and polystyrene balls to represent the moon. The students' heads will represent the Earth in this model. You'll want to darken a large room, get students gathered around as close as they can to the sun. They'll need to put their arms out at full length and be able to make full circles. So that's the kind of spacing that you'll want to be able to achieve. For the moonballs activity, you'll need a light bulb to be your model sun. Incandescent is best with an unfrosted bulb. And you'll want to have some kind of lamp fixtures that you can attach to an adjustable stand. It's really good to try to get the height of that light bulb right at the average height of your students. But you'll want to be careful, of course, because it's a very bright source. So, tell your students to try to avoid staring right at the light bulb. For the moonballs themselves, you'll want to get a polystyrene ball with some kind of pencil or skewer. Polystyrene is kind of a more compact version of styrofoam, and it has a smooth surface which reflects the light a lot better and is a better model for your moons. It also doesn't flake off the way styrofoam does, and so they'll tend to last a little bit longer in your classroom before you have to replace them. Your students will, of course, want to bang this on everything. You'll probably want to discourage that as much as possible because that will shorten the lifetime of these and also causes lots of disruptions, of course. And then you'll want probably to have an extension cord to run power to your lamp. Just be careful to tape it down with some gaffing tape. Gaffer's tape works well because it comes up really cleanly. This light bulb in the center of our circle is representing the sun, okay? What ways is it like the sun?
Bright.
It's bright, okay. What other ways is it like the sun?
It's in the middle of all of us.
It's in the middle? Oh, okay, like the sun is in the middle of the solar system, sure. Are there some ways in which it's not like the sun?
It's very close to us.
It's very close to us, right. Yeah, the sun is pretty far away. What other ways is it different from the sun? It's very small, right? It's very, very small. The sun is huge. We can fit 1 million Earths inside the sun. So how is the Earth different from our heads?
Much smaller in relation to the sun.
Right, yeah, we've got this kind of scale thing going on here where our heads are bigger than our model sun, but it's the opposite, right? We could fit 1 million of our heads inside a model sun. All right, friends, we're going to continue our model with one additional complication, we'll call it. We're going to add in the moon. And so these little balls are going to represent the moon. The model isn't great in that this moon should be much farther away from the Earth in order to be accurate. But this is going to work for us to demonstrate phases of the moon. All right, so the moons we'll hold out at arm's length, and let's start out with our moons just a little bit east or left of the sun. So as you're looking at this model moon, you can see a little bit of the day side of the moon. And remember that we had day and night on Earth, right? The side of Earth that's facing the sun is day. The side facing away is night. The same is going to be true of our moon. The side facing the sun is day on the moon. The side facing away is night. When we're just a little bit off, we can see just a little bit of the daytime part of the moon. And what shape does that look like to you?
Croissant.
Like a croissant, yeah. A fingernail that someone just clipped off. Yeah, so croissant is French for crescent. And those are crescent rolls. And so that's the shape. And so we sometimes call this a crescent moon, or we always call it a crescent moon. If you move it a little bit closer to the sun, you'll see that the moon gets really, really small. And then if you move it further to the east, you'll see that crescent gets fatter. The direction that the moon moves around the Earth is the same direction that the Earth spins. And so it's to the east. So if you see the moon in this orientation relative to the sun, it's getting bigger. Does anyone know what the special word for getting bigger is? Waxing, great, yes. So the moon is waxing, it's getting bigger, and so we call that a waxing crescent moon. And so you'll always see that to the east of the sun. All right, now we'll move our moons all the way over. Let's keep going eastward until we hit a point where we see it about half of the moon. All right, so move your moons to that point. Now, when you see half of the moon, you're only seeing half of the day side, right? And so you're kind of seeing half of a half. So we might call this a quarter moon. And in fact, we do. We do call it a quarter moon, although we don't call it for that reason. We call it a quarter moon because it's 1/4 of a trip around the Earth, not because we're seeing just a quarter of its surface. But we are, so that's a fun way to remember it. You're seeing 1/4 of its surface, so it's a quarter moon. Now we continue the moon's motion around the Earth. It's a little bit past quarter, so it's a little bit bigger than a half, but not quite a full circle. Does anyone know what kind of silly name we have for this moon? Gibbous. That's a gibbon. The monkey is the gibbon, and actually it's an ape, but I sometimes do jokingly call this the monkey moon. So it's a waxing gibbous because it's getting bigger, closer and closer to full. And then if we continue our moon's motion all the way around the Earth, we want to keep it in the sunlight, so you want to avoid putting it in the shadow of your head, the shadow of Earth for right now. So you may need to hold it up high. And you'll see now the full circle of the moon. And so this is the full moon. So the full moon is opposite the sun with respect to Earth, right? The sun is on the other side of the sky from the moon during its full phase. In fact, let's think about our previous example of Mount Nose and West Lake Erie. So let's think about West Lake Erie. What time of day is it for West Lake Erie right now? Sunset, right? Because it's midnight at Mount Nose. And so where is the moon at sunset when it's full? Is it just rising or is it setting? It's just rising, right? And so it's just coming up. So at sunset, the full moon rises. And think about East Lake Erie. Where is the moon for it? The sun is just coming up, and where is the moon? The full moon. It's setting, that's right. So the full moon rises at sunset and sets at sunrise. They're opposite each other. Let's continue on. We'll now make another type of gibbous, but now it's getting smaller. Does anyone know a special name we have for getting smaller?
Waning?
Waning. So this is a waning gibbous moon. We can continue on till we hit another half moon, half of a half, which is a quarter. And this is the last quarter moon, because it's the last quarter of our trip around the Earth. And then we can continue on with a waning crescent as we get closer and closer to the sun. And then if we put our moons right between the Earth and the sun, but don't quite block it out, so you can put it either above the sun or below the sun, now the day side of the moon is facing entirely away from Earth, and we only see the night side of the moon, so it means we can't see it. So does anyone know the name of this moon? This is the new moon. It's the moon that you can't see. All right, so we've got our phases of the moon all worked out, and we can see how the phase of the moon depends on your perspective, the direction that you're looking at, and how much of the daytime moon you're seeing. Let's move it, in fact, back to that waxing crescent position. And I want everyone to first look at your waxing crescent, and then look at everybody else's moon around. What phases do you see? Call out some of the phases you see.
I see a waning crescent.
I see a gibbous moon.
I see a quarter moon.
I see a waning gibbous.
All right, so we can see all the phases as we look around the circle because we all have different perspectives on the amount of daylight that we're seeing. And so that's how we can see that the phase is just a matter of perspective. The last thing we can do with our moon balls is we can model eclipses. And the first eclipse, which I already kind of mentioned just to avoid, is to go back to the new moon. So we put the sun directly between Earth and the moon. and then block out the sun with your moon so that you can't see it. In fact, let's make it easiest for you. So just close one eye and block it out. Now, the moon is blocked to the sun from your view. This is an eclipse of the sun by the moon. The moon is blocking the sun out. And look around the circle at where the shadow of the moon is on the other Earth's faces. Where is it? It's on their eyeball, right? And are there places on their face where there isn't a shadow? Yeah, there are. Those places. In fact, switch your eyes. Without moving this with the moon, switch your eyes and be careful. You got blinded, didn't you? That's because the other eye was in sunlight, and so it was not experiencing an eclipse. And so this is a pretty decent way of course, the model isn't great in that this moon should be much farther away from the Earth in order to be accurate, but we still are getting the effect that the shadow of the moon is smaller than the Earth, which means there are places on the Earth which won't see the eclipse. Now, the other type of eclipse that we can model is when the moon goes inside the shadow of the Earth. So let's go back to the full moon. We'll turn all the way around. But instead of going up above our shadow, let's actually just put our moon directly into Earth's shadow. This is an eclipse of the moon by the Earth. And so the moon has gone into the Earth's shadow and it kind of disappears. And you'll notice that everywhere on the night side of the Earth can look back and see the moon is in the shadow. However, there is half of the planet that is facing the sun, right? Everywhere that's in daylight, they're missing out on this cool eclipse. But everywhere that's on the night side sees the moon in the shadow of the Earth and has seen it disappear. So those are our phases of the moon. Are there any questions that you may have?
Yeah, I'm wondering why with a lunar eclipse we see a red moon.
Oh, a great question. So as sunlight is passing through Earth's atmosphere, blue light is scattered into random directions, leaving only the red light to bend into the shadow. So when the moon passes into Earth's shadow, we see only the red light from the sun hitting the moon. And so that red light lands on the moon that's in the shadow, and we see a red moon. Some cultures call it the blood moon because of its color. And it's very interesting. When you watch a lunar eclipse, the amount of red light is pretty dim. And so when there's some amount of the moon that's still illuminated fully in the sun, it's so much brighter that you don't notice that red color until the whole moon has disappeared into the shadow, and then you can see now just the red light that's there. One of the ways I like to think about it is that it's actually the light of all of the sunrises and all of the sunsets on the Earth is hitting the moon.
Why can't we see the eclipse every month?
This is a great question. Why don't we see an eclipse every month, right? Because we had the moon go right in between, and why isn't every single new moon in eclipse, and why isn't every single full moon in eclipse? And the reason for that is because the moon's orbit is not in the same plane as the orbit of the Earth around the sun. So if they were in the same plane, then indeed every single new moon would be an eclipse. Every single full moon would be an eclipse. But it's tilted a little bit, which means it kind of goes above and below the sun. And so most months we're missing it. And I'm exaggerating it here as I spin around because my head is very big compared to this moon and very close. And so if we were making this model more accurate to scale, I could get it closer to the real angle, which is only about 5 degrees. So it's a very small angle. The size of the moon and the sun in our sky happen to be almost the exact same size. They're both about ½ a degree in our sky, which means that 5 degrees that the moon is above or below the sun is actually pretty big compared to the size of those two objects. So most of the time, we don't get eclipses. So eclipses are relatively rare events when it just so happens to line up just right. Which for lunar eclipses, that can be on average maybe one every year or so. And for solar eclipses, it's maybe like one every year and a half that we get a solar eclipse somewhere on Earth. A really cool way to do the moonballs activity without the sun being the light bulb is to do it in the real sunlight. So if you've got a nice bright sunny day, you can take your classroom outside and you can have them form a circle, though it doesn't need to be a circle, any shape will do here, and then have the real sun be the sun in this model, and then they can use their moonballs and they can do this activity in the same way as they were doing it indoors. The really great part about doing it outdoors like this is that if the moon is in one of the crescent phases, or if the moon is in the sky during that time, when you hold the moon in the same position to match that phase, it'll be right behind it. And that's really cool. If you're going outside to use the real sun for this activity, please remind your students to not stare at the sun, because it is dangerous to look at. The ultraviolet light from the sun can damage your retinas. Thank you for watching our tutorial video about doing moon phases with the moon balls activity. And if you'd like to see a kind of a nice activity to act as a predecessor to this, you can check out our video that is called Mount Nose, which has the same setup, just doesn't use the moon balls. And for other activities about space science, you can check out the Space Weather Explorers Week websites, and the links for those are in the description below.